Hello, everybody. I'm back again to talk about more chemical kinetics, this time with emphasis on reaction mechanisms. For those of you going on to organic chemistry, you'll hear a lot about mechanisms. We're just going to introduce a lot of the terminology and ideas associated with this course. This is a very intensive topic, so this is more of a conceptual and qualitative talk, less mathy than what we did before. So what we've been focusing on all along is, such as shown right here on the bottom, we've been writing for the whole course overall reactions. For example, you could observe in nature that there's a 2-to-1 stoichiometry between nitric oxide and elemental oxygen forming NO2, and then you could balance out an equation. You could have two NO2 molecules. Let's say this is a gas phase reaction, and this is something you could measure. You could start off and have a system where you have a certain stoichiometry, a certain amount of nitric oxide, a certain amount of oxygen, and observe this product forming, and you could figure out the stoichiometry by a lot of the methods we used earlier. Well, basically last semester was a lot of emphasis on that when we talked about chemical reactions with stoichiometry. So this is really good stuff. That's an overall reaction, and all the kinetic expressions we've been doing so far have dealt with coming up with rate laws associated with overall reactions. And one of the things that we said early on is we don't know, for example, for this, the rate law is going to be something in the form of K and O to the M and O2 to the N, where M and N are orders, but we don't know what those orders are, and there's no definitive relationship when you look at the overall reaction and you have the stoichiometric coefficients of the balanced form of 2 and a 1, that's going to be a 2 and a 1. If it is, it's strictly by coincidence. So that would be just a generalized expression. We'd have to do experiments to figure out what M and N are. It could be that they're both 0, it could be this is 1 and 0, it could be 1 and 1, and so forth. So what a mechanism is basically a series of steps. We call these elementary steps. I can't spell too good. Elementary steps. This is a relatively simple mechanism that build up to give you the overall reaction. It's kind of what we present or we project or theorize is going on behind the scenes to give you this overall reaction. There could be some experimental evidence. Sometimes there's ways of detecting certain species that are formed in situ and so forth. There are other inference that comes out of it. So these two steps that I show here are called elementary steps. And one of the things you'll notice is that if you add these reactions together, they give you this product because the N2O2, the dinitrogen dioxide, cancels. This, I'll just put a little light line through it. These two cancel, giving you 2 NOs on this side, 1 O2, and then 2 NO2s. And this is balanced, 2 nitrogens, 2 4 oxygens, 4 oxygens. So this mechanism looks reasonable from what I can see of it so far. And so one thing in terms of our terminology of mechanism, see how this is, the N2O2 is formed in one step, it's formed over here, but then it's consumed or reacts in the next step and is gone. It's not, doesn't show up, it's kind of formed and then the next step it's consumed or reacted. And so we call that, N2O2 would be the intermediate. We call that an intermediate. So intermediates are a new term, but they're something that shows up on one step and is consumed or reacts in the next step. It does not show up in the overall equation. So we call that an intermediate or a reaction intermediate. It's the same thing. And so the sum of the elementary steps, here it's a pretty simple mechanism, is the reaction mechanism. That's the terminology we use when you take organic chemistry. I assume many of you will. If you don't, that's fine. But if you do, you'll be studying a lot of reaction mechanisms. That's a big part of the course. For here, we basically just introduce it. Some of the terminology we use here is we deal with things that deal with the molecularity of a process. In both of these cases, we would consider these bimolecular reactions. There's two reactant species on each step. Also, there are other cases. For example, there's a unimolecular. If you have a step that looks like just going from A to products in a mechanism, that would be unimolecular. There's one species, it could be a molecule or it could be actually an atom or an ion. That's called a unimolecular step, and these are both bimolecular. It turns out in mechanisms that almost exclusively they're either unimolecular or bimolecular. There is a few cases of termolecular where there's three things. They're so rare, we're not going to talk about them. There's only a few reactions that have observed like that and nothing beyond that. One of the things that's different, I have to erase a little bit of this, about elementary steps for a mechanism versus an overall reaction. What I said before for the overall reaction holds. We cannot, I erased it unfortunately, when we have the overall reaction, there's no relationship between the stoichiometric coefficients and M and N. If they do end up being the same, if this ends up being a 2 and a 1, that's coincidental. Conversely, you can write rate laws for elementary steps directly, maintaining the order of the species. So for example, in the case of step 1, the rate in step 1 would be NO squared. There's two nitric oxides, and for example, in step 2, that other bimolecular reaction, we can write that as K N2O2 times O2, where they're each raised to 1 power. The overall order is second, but it's what I would call a type 2, where you have first order in one species and first order in second, as opposed to second order for one species. So you can write rate laws for elementary steps. These are elementary steps. They're not overall reactions like this, so they're different. One of the things that becomes critical in particularly in subjects like organic chemistry and biochemistry, where this comes into play all the time, is you have some principles that carry forth. One is when you have a mechanism proposed for a given overall reaction, which is usually what you'll observe in the lab most readily, is that the sum of the steps, when you add them together, just like in this case, have to equal the overall reaction. The other thing is that, and this is a very much an oversimplification, is that sometimes what we have is a whole host of steps, and one step is much slower than the others. The slow step is the rate determining step. Do we have cases where we don't have an appreciably slow step relative to the others? Yeah, they're very common. This type of analysis that I'm presenting is presented in the simplest form to give you a good idea about it, so you can go on to other study things where it becomes much more complicated rather quickly. So we want to get the foundation down. So let's go through the example. If you do want to follow along in the notes, this is actually starts at around page 18. I'm going to work the example exactly from the notes because this is something, it's less mathy and more conceptual, and I want you to really get the idea here with something you can go back and read, as opposed to your math where you can try to strive for a numerical answer. You can ask an AI and so forth. If you get stuck, you can email me. But with conceptual things, I think they're actually more challenging because it involves more understanding. So let's take, I'm on page 18 if you're following the unworked out note sets. Here's an overall reaction. It's all in the gas phase. You have H2, two ICLs. We have it going to 2HCl gas. Everything's a gas, and I2 gas. That's an I. So that's the overall reaction. And experimentally, somehow they've shown, maybe using the ratio method of initial rates that we did, that the rate law is given by K times H2 times ICL. It's second order overall, and it's first order in H2 and first order in ICL, what I would call type 2 second order. So there was a host of mechanisms proposed, and let's see which one, I'm not going to say is correct, but I'll say which one supports this, because it would take, you don't really ever prove a mechanism, you only really disprove them, and you just basically gain more support for it. We're at the stage in the game now, we're able to see things better molecularly, what's going on really quick time scales. So we're hammering down, getting close to having closure on mechanisms, but it's still something with a little bit of a question mark. So let's see which ones do not work. So let's take some proposed mechanisms. Some scientists were sitting down and they're proposing mechanisms. So mechanism one that was proposed for it was step 1 was ICL plus ICL. I'm going to put this down here, going to I2, and let's see here, Cl2. And we're told this step is slow. The first step is slow. The second step, step 2 in the mechanism, is Cl2 plus H2 going to 2HCl. Everything's in the gas phase. I'm not going to keep writing it out and make my H a little more H-y. So let's look at this. It's one of the things, all you have to do is nix or show one of the things isn't correct. Does it A, does it sum up to B, the overall reaction, and B, does the rate law predicted from the mechanism correspond with the experimental one? In this case, just looking at one of those, the slow step is this step right here. Step 1 is slow. We're told that. How slow is it? I don't know. We'd have to have numbers to it, but we're told it's slow relative to this steps, relative to step 2. So when we write the rate law for step 1, I'm just putting a little subscript here to tell me if it's from step 1. It's going to be K for ICL squared, because you can think of it as two ICLs coming together. That, although it is second order, it's not the same type of second order. So again, I'm using the property that when you have elementary steps that you can write rate laws directly, you can take the order here, which is second, the coefficient here is a 2, and you can make that because it's an elementary step. It's showing actually what's going on a molecular level. So this does not work. It does not match the experimental form of the rate law. So that mechanism does not look good. Good to try, but not too good. So mechanism 2, and again, if you're following along, it's on page 18 going into 19. Mechanism number 2 is step 1 is H2 plus ICL going to HI plus HCl, and this is slow. And step 2 is ICL plus HCl going to HI plus Cl2. Everything's in the gas phase, just like before. First thing is this is a slow step, so the slow step is the rate determining step. So step 1, the rate, we can say a rate law would look like K, and then we have H2 to the first power. There's a 1 here, you can imagine. And ICL, well, that's good. That checks a box. This agrees with the experimental rate law. But let's take the other factor. If we add these reactions together, let's see here what cancels, if anything. The HCl cancels, so we end up with H2 plus 2ICl going to 2HI plus I2. Okay, we got H2, H2, 2ICl. That looks good. Oh no, this isn't good here. We got 2HI. Did I do that right? No, it'll be a Cl2. Excuse me, when I add these together, this will be a Cl2. Still isn't right. We got, instead of H2 HCl's and I2, we got 2 HIs and Cl2. So it's not the same. It's not the same. Add them together and show that, so it doesn't pass that test. Mechanism 2 started off pretty good, ended up not looking too good. So I would not consider that from this information to be a good candidate for a mechanism. So far, so good. So 2 losers. Maybe we have a winner in here. That's something that looks plausible. So let's go to mechanism 3. I'm on page 19 now in the unworked out notes. Step 1, H2 plus 2H. Oh, H2 goes to 2H, and that's slow. Right off the bat, you can read the rest of it in your notes. I'm getting rid of this. The other steps below this are 2 other fast steps. Step 3 is fast relative to it. Step 2 is fast, and step 3 is fast. Right off the bat, I don't have to keep going, because what I'm seeing is that the rate given by the slow step is going to be equal to K times H squared. It's nothing like what we have here. They have no ICl. It does not work. So I'm not even going to write the rest of it out on an exam. You can look on the sheets for the rest of the steps. I take the shortest but correct route on problems. This one is nixed right from the start. So let's do the last one. Hint, it'd probably be a good example, teaching method for me to have one of the mechanisms be correct. So in the final mechanism, step 1 looks like, watch that it isn't, H2 plus ICl goes to HCl plus HI, and that's slow. That step is slow relative to the second step. The slow step is kind of like the stoplight that controls the rate of traffic. HI plus ICL goes to HCl plus I2. So we have that. First thing is step 1 is the slow step. So the rate is K, first order in H2, first order in ICL. That looks good. It matches nicely the experimental rate law that we got from doing a study. Let's add these reactions together. The HIs cancel. So we're left with H2 plus 2 ICLs. Looks good. Goes to 2 HCl's. And then we've got I2. I2. So that looks good as well. This matches. So this, I am not saying that this is definitively the correct mechanism, but what I'm saying is it's plausible. It's plausible. And we would do more studies. Maybe we can detect, let's look at this, the intermediate in this. HI is the intermediate. Maybe we could detect that in this reaction, for example. That's one of the things you try to do. There's a more complicated case below this, mechanisms with a fast initial step. It's another series. I am not going to test on that. I put it in here for completeness. It's more complicated. For those of you going on to organic chemistry, look over it. I actually have worked out within the note set itself, the main set of notes, the problem associated with that, so you can work along with me and get the gist of it. It will give you a heads up for organic chemistry and biochemistry and courses like that. if you're taking those, that might help you. I would say it would probably be harder than something you'd see like on an MCAT or something like that. But these are some of the things to know when you look at mechanisms. That's what we covered so far. Identify intermediates. Understand that the rate determining step is the slow step. If there is a slow step, and you say, well, if there's not, well then it runs to more complicated analysis that goes beyond this course. This is an introductory course. We had cover a whole range of things. Understand that the sum of the elementary steps gives you what we call a mechanism, and that they have to add up to be the overall reaction to see if that agrees with what you see with the experiments. And when you're comparing your proposed mechanism to an overall reaction that you've observed in the lab, is that the rate laws have to match, and you can write the rate law directly from the elementary steps, with the rate determining one being the one of the slow step. And then also the overall reactions have to match. So those are some of the constraints. Is it more complicated than this? Yes. This is courses of material, literally, that could be taught on mechanistic analysis just of organic molecules. And so, let alone inorganic, which could be other courses as well. This is a big chunk of chemistry, so we're getting the idea. We will wrap up the notes on the next set with a short video on catalysis and catalysts. And so we'll talk about that. And on this note, I am done. I hope you enjoyed the video. Take care.